mathematically, it's very easy. So it's the foundation of one of the gimme questions that'll be on the next test. So you'll like it, at least figuring it out. Doing stuff with it is a little bit of a different story. But talking about the dot product brings us to terms like orthogonal, and then later on in the course orthonormal, and so on. So, eigenvalues. The dot product of vectors u and v, dot product, I'm just making sure my grammar's right, is given by the sum of the products of the components. All right, so basically, all you're doing is multiplying corresponding components and then adding the results. All right, so very straightforward. I did hit record. I always have to double check because I've done that before. I did it with I'm trying to remember. Oh yeah, it was. I think it was calc. It was either calc for business or calc for business. It was a fire drill that happened in the middle of class, and I was like, you know what? Let me hit pause on this video. The video was like 2 hours long, and it was something that was like critically important. I accidentally hit cancel, wiped out the whole thing. So there was that. The fire drill, 2012. Then the power went out one time in the middle of a video, so that sucked. Also, and it's always the really lengthy ones. But then there's the other times where I just forget to hit record, and I'll just ramble on, and I'll be like, I'm emphasizing points, and I'll be on a roll, and I'll feel really good about it. And then a student will raise their hand and say, "Are you recording any of this?" And be like, I don't know. But then the worst, I think, was last semester or last session. I think it was either semester or session. I can't remember. But it was Calc 3. So this is me confessing something that you may not have already known if you were in my Calc 3 class. I recorded an entire lesson, and I got a message from a couple of students saying, there seems to be something wrong with the audio. And it was because I was recording the entire lesson without having the mic plugged in. And about like 75 or maybe 90% of the way through the lesson, I was like, oh, the mic is not plugged in. So I was like, all right. And then I just kind of slipped it in. And I didn't say anything because I couldn't deal with that kind of heat. So it's just so bad. So if it's like ruining the flow because I'm checking constantly, it's because of all of those instances or incidents that happened in the past. So U dot V, 3 times -1 plus 5 times 3 plus 2 times 0. Equals 12. Yeah, I think. Let's get a little plus sign there. It's a dot. It's a dot up here. I don't think any of you are going to ask this, but it is a form of multiplication. And people have asked in the past, so I feel the need to mention it. The question was, do we have to use that particular symbol? Can we represent the multiplication in other ways, like with parentheses or with an X? And the answer is, it's called the dot product. So what the hell do you think? Now, I mean, aside from that, the parentheses approach implies traditional forms of multiplication, like a scalar multiple. Also, since some vectors, some people, textbooks, even GeoGebra, uses rounded parentheses to represent vectors, that could become confusing. The X multiplication symbol between two vectors is something called the cross product, which we're going to get to. So it's something different. All right. So we have a need to represent it this way, but also it's called the dot product, so we should do it that way. Now, when you're actually multiplying numerical values, it, I suppose, doesn't really matter which one you use. I'd stay away from the x, only because, I mean, how often have you used that since like second grade to represent multiplication? Right? Just out of habit, you probably wouldn't even think to use that. Right? So, and also, I mean, a variable x could sneak its way into some of the stuff that we do. So, you know, just stay away from that unless you're dealing with a cross product. But when you're dealing with the expanded form of the dot product, a dot or parentheses, either way is fine. But why not just use a dot for consistency? Right? Dot product and scalar product are sometimes used synonymously. Sometimes they're not. So we'll deal with instances in which they're not. But in this context, they are, because we're finding the scalar product of two vectors. Right? A scalar product involving a vector and something else, something numerical, may not take on the same form. So this is saying find the dot product of P and Q. So -10 times -2, yeah, plus -4 times 1 plus 7 times 6. So 18. You tell us, you made the problem. I don't know. I think. You could always check it with the calculator in a much more complicated fashion. So big. All right, so squiggly brackets. Now, there's two ways to handle this. Let me do it the way that doesn't require you to remember any special functions first. All right. So your components 10, -4, and 7, separated by parentheses within the squiggly brackets. All right, so it gives you the product of each of the components. Right? Honestly, it doesn't even know that you're dealing with vectors. It knows that you're dealing with an array of numbers, and that you want the corresponding components multiplied. It's not trained to think of it as as particularly a vector. So what you can do is then just manually add this up. Another thing that you could do would be to use the sum function. Right? So, and I think I haven't tried this yet. Yeah. Okay. Another thing you can do would be to store it into a list and then find the sum using the sum of that particular list. But if you go back to what we did originally, this guy here, and just around it, apply the sum function. So second stat, if you go to math, you get the option 5, which is a sum. Sum of all that stuff. Second left arrow brings you all the way to the beginning. Second right arrow brings you all the way to the end, if you don't want to scroll, which I don't. So, yeah, a little bit more complicated. I mean, you start throwing in fractions and radicals and things like that, then maybe it's worth your time. Zeros seem to mess people up. I don't know why, myself included. For some reason, on a test, this product is going to become a 2 for like a third of the class. I have no idea why. I can't explain why I do it sometimes, so like I really genuinely do not know. I have no idea why that happens. It's just a brain cramp, I guess. So maybe just to check your work. But then again, the odds of you remembering this as opposed to that. I'm just trying to think of like the structure of a program. Yeah. If I have time later today, maybe I'll write a program and show you how to do it tomorrow. Next week. Because again, it's really more quality control than anything else. It's not for the purpose of actually, getting the concept down. The concept is very simple. It's so that you don't give away free points on a test. All right, properties of the dot product. U, V, and W are vectors and C is a scalar. It's commutative, which is great, because the cross product, when we get to that next week, is not commutative. It's actually something known as anti-commutative. Associative property, that's wonderful. All right, so you can associate your scalar with either component that is being dotted, which is good news. Distributive property, and it works the way distributive property always works. Property of magnitude is pretty cool. All right, so if you take the dot product of two vectors that are the same, it'll be the square of the magnitude. So just snag a quick example like that. Just taking what I had written above. All right, so U dot U would be equal to 3 times 3 plus 5 times 5 plus 2 times 2. All right, each component multiplied by itself, which is the same as 3 squared plus 5 squared plus 4 squared. 2 squared, sorry. Right, which is actually what you would get if you wanted to find the magnitude of U and square it. It's not really a proof, it's more of a justification. But it gets the idea across. Because if I wanted to find the magnitude of U, it'd be the square root of this squared, that squared, and that squared. So we got this squared, that squared, and that squared right here, not under a root. How do we get rid of a root? Squared. So the magnitude would have the root. You want to get rid of the root, square it. So square the magnitude, and you have it. Right? If you wanted to do it in general terms, you got this guy. All right, 3 components of my vector U. I'm going to dot this. u dot u would be equal to u1 times u1 plus u2 times u2 plus u3 times u3, which is the same as u1 squared all right. These themselves are not vectors, they're only components of vectors, so they can be squared. We wouldn't be able to just square u, we'd have to square the magnitude of u, which is what's going to happen next, right? So I would want to define this as the magnitude of u. The way to do that would be to take the square root of it and square both sides, and we would get this, which we already know is the same as the dot product. Fun little proof, right? All right, so if you don't get it down, that's all right. It's going to be saved, provided power doesn't go out or something. Recorded, etc. But, I'm not saying this will be the proof that'll be on the next test, but there's always a proof. Maybe it's this one, maybe it's something else. We'll see. So these examples you can do for practice. Because I got 3 other properties here to play with. Some of them are easier than others. I mean, if I ask you to prove the commutative property in R3, because all of this is R3, it's 3 components of the vector. If I ask you to prove the commutative property, that's pretty straightforward, because all you have to do is show that the result of each of these dot products are going to be the same. That's not that would go under or in the category of a gimme, I think. That would be really nice. This one, it's still not bad. I mean, I just walked you through it, so it shouldn't be too crazy.